Our speaker Dimitris Gerontogiannis from IMPAN, and he will talk about ideal quantum metrics from fractional Laplacians.
Thank you. It's always a pleasure to give a talk at your seminar. So today I'm going to present work that I did with Bram Mesland from Leiden University. And it is about some optimal transport framework for dynamical systems. And in fact, the phase spaces might not be so regular in terms of differential geometry. And therefore, we get into the realm of fractional Laplacians on metric measure spaces in order to make sense of this optimal transport framework. So at first, I will give some background on this optimal transport and what we want to do, and I will make sense of the quantum metrics as well. And later on, I will talk about how to work in this metric measure setting, and later on how to implement dynamics, that framework. All right. Yes, here. Well, I will not say, however, too much on optimal transfer. But the main idea is the following, that this started as an applied problem, okay, an optimization problem back in the late 1700s by Monge. And the idea was he was trying to understand how costly it is to transport a mass from one place to some other place, okay? And one can realize this problem as transporting probability distributions, because you can just normalize, and of course you want the mass to be preserved when we transfer it. You don't want to lose or to add something. And so you can just care about probability distributions on the space of probability distributions on the space. Okay. And you just want to move them around and to find a quantity that says how costly it is to move from one place to the other. And the optimization problem is about computing this infinity. Okay, and here you have the cost function. Usually you can just take the metric or powers of the metric, and then you integrate over probability distributions with marginals, the two distributions that you want to compare. And many years later, in the 1940s, Kantorovich and Rubinstein, they found a dual formulation of this problem in terms of the supremum. And in the book of Villani, there is a very nice explanation, like why we use a cost here and what really means the supremum, but I will not talk about this. Just look at the intro. That's a very nice thing. Now, the supremum here, again, it gives a metric, and the supremum is over, it's the supremum of the following quantities. So you take Lipschitz functions in your metric space with a uniform upper bound on the Lipschitz, right? And then you evaluate the measures from that function f. So basically you integrate the function f with respect to mu, and you subtract the integral with respect to mu. Okay, and then you take the supremum, this gives a metric. And the interesting part about this metric is that it's not just any metric in the space of probability measures, one that generates the weak star topology in that space, the pointwise topology for measures. And like about 50 years later, Alan Kohn observed the following.
Excuse me, if you use another function,
Yes.
how does the theorem look?
The same. But here you would not have like the Lipschitz constant, but you would have the equivalent of the cost function. Like how do you define the Lipschitz constant? It's f of x minus the supremum of f of x minus fy over the distance. So in place of the distance, you would have the cost function. And so you would require f of x minus fy to be less than or equal to the cost.
Don't you need some assumption on the cost function for that to work?
Yeah, you need some assumptions. You need something. Yes.
It's always fun.
Yes. Yes. But here we will deal with the method. But so 50 years later, Alan Kohn, I mean, he produced. He started the philosophy of noncommutative geometry, which is a framework where one tries to implement differential geometry techniques to mathematics adjacent to quantum mechanics. So there's a lot of algebra in that setting. But here's the observation. In particular, if your metric space is a compact Riemannian manifold with some additional structure that guarantees the existence of a nice differentiation operator, a differential operator in the manifold. And you equip the manifold with the geodesic distance, then you can realize the Lipschitz constant of any function of that manifold with the geodesic distance as the operator norm of the commutator. So what's the commutator here? The commutator for a commutator. So you have the function f and acts as multiplication operator on L2 of your space. And so if you take any function g, like nice enough, like Lipschitz or Snoop here, this would be d f g minus f g. Okay, and the operator norm is the supremum norm. Okay, and this really, if you just go to this formula, you can simply focus on Lipschitz functions, and you can replace this part, the Lipschitz semi-norm, with the operator norm of the commutator. Okay, so you might think, okay, why should we do this? Well, because this offers a way to generalize. Because the whole program of Alan Kohn was about finding differential operators on very abstract frameworks that might not be manifolds, or on dynamical systems, for instance. And so the idea is that we try to find, to replace, I mean, you have differential operators, and here you might no longer have multiplication operators, but you might have some convolution type operators. Okay, so it offers a way to generalize these Monge Kantorovich, Monge-Kantorovich metrics. But I will come back to that. I'm sorry? Spin, it's something that guarantees the existence of a differential operator that has nice properties. You will not define. No, we will not need this. We will not need it. And so here's the way to generalize this, like around the same time, a bit later, maybe a couple of years later, Mark Weyl generalized Kohn's observation to the general setting of cipher algebras. And what is a cipher algebra is, I mean, also Tatwamasi talked about this last week, and it's a collection of linear operators on a Hilbert space, which are bounded with for the operator norm. Okay, so you can view them as like infinite matrices with which are bounded with control on the on how much the entries grow. And then you want this collection to be an algebra over the complex numbers. And you also want it to be closed under taking adjoints, and also to be a closed under the operator norm. And therefore, if you start with any system algebra and you focus on dense subalgebra, so this system algebra, like in your mind here, you can have like the continued functions on the manifold, and A to be the smooth functions on the manifold, math out A. Then you focus on semi-norms, which are invariant after taking the adjoint. So the semi-norm applied at the adjoint of an element is the semi-norm of that element. And you also want the kernel of the semi-norm to be the constants, right? And then you can write down a Monge-Kantorovich metric as before, where now, I mean, these are your smooth or Lipschitz functions, and you can view this as, you know, some abstract Lipschitz semi-norm. And you also want this to be less than or equal to 1, and you get this quantity. Now, this is going to be a metric, it satisfies the properties, but it might obtain infinite values, okay? So you might find like probability measures with infinite distance. But as soon as we know that this metric generates the Wixar topology, then this metric will be finite. Because the space of probability measures, or the state space of the system algebra, is compact with respect to the Wixar topology. So you have a metric generating that topology has to be of finite diameter. And I mean, you don't need to understand what the state space is, but it's like probability measures, okay? And it's functionals in the system algebra, and that's state 1 to 1, and they are continuous, the units. But for now, it's like probability measures. And if you have system algebras coming from dynamical systems, they can also have like probability measures which are invariant. Okay, so I mean, system algebras they can really be used to study dynamical systems, to represent, in fact, dynamical systems on Hilbert spaces. And it really starts with the Gelfand's duality back in the 1940s, where it basically identifies topological spaces with commutative algebras. So if you have topological space, you consider the continuous functions of that space, and you get multiplication operators on L2, okay, with respect to some random measure. And now if you have commutative system algebra, you look at the irreducible representations on a Hilbert space in this form topological space that will give you back this, okay? And now using this philosophy, you can basically consider like group actions on spaces, and then you try to form a system algebra out of these. Now, elements in here will, informally speaking, will be like functions from the group gamma with coefficients in C of x, okay? So if you write them down, there will be polynomials on gamma with coefficients C of x. And if you take closures, you will have elements that get approximated by these. So it's like Fourier expansions. And if x is 1 point, then you just have functions on gamma with coefficients in complex numbers. And if gamma is trivial group, then you just have C of x and you have multiplication operator. And you can also do something analogous for foliations, like stable and unstable foliations in a manifold. And there is a way to represent this structure as convolution operators acting on the Hilbert space. And you can convolute along the leaves. You cannot multiply elements that encode different leaves. Okay, so these are the algebras that might appear in the end, but for now we will just deal with just spaces. And the spaces will be some fractals. Okay, of course. All right. But before going there, some examples, because since the definition of real and false observation, people in non-computative geometry world, they have really tried hard to find interesting examples where you have like maybe a dynamical systems and one Kantorovich metrics. And indeed, I mean, this is not a complete list. But you have like spectral triples for the gasket, for instance, like I didn't define spectral triple yet, yes, but like Monge Kantorovich metrics for the surface gasket, for hyperbolic groups, quantum tori, one-dimensional solenoids, quantum spheres, like deformations of spheres. But there are several open problems there because I mean, it's a new theory, relatively new theory.
Just to clarify, so the list, for example, in which you have the sister algebra for which you get
you can find some semi-norm either through some differential operator or with some other technique, because this definition of real does not necessarily say that the semi-norm should be of that form. It can be whatever. But of course, people are interested more in this because you have more information to work. But two problems kind of remain. And one of these, two of these are like, how much can we generalize Cohn's observation? Like, how much can we go outside of the realm of Riemannian manifolds to obtain Monge Kantorovich metrics? What can we do for metric spaces, for instance? And can we do it in a natural way, not in some abstract way, so that this structure of differentiation that will give us this Monge Kantorovich metrics sees something about the metric structure and gives something, and in addition gives something new. And
what would be like a good goal? Are you looking for invariance? What's the end goal? Do you see something?
that was, in fact, an abstract question of Riefel in one of his first papers, but I think it was giving direction. But one good goal would be like, can you construct differentiation that will give you Weyl laws? Like you can have asymptotics, spectral asymptotics of your metric space. You can read information about your metric space through spectral asymptotics. Can it be compatible with dynamics on that metric space? And stuff like that.
Just maybe one comment. Just one example you can think of, even like this first example that Dimitris mentioned, like spectral triples and fractals, etc. So you can even take a Cantor set that it doesn't have kind of obvious differentiable structure.
Yes.
But the thing is that you can reconstruct the metric by defining some differential operator here. So essentially the question is probably, how far does it go? Like,
Yes.
you always do something like this.
But in a way that you don't go abstract, and so that you can still do geometry. And the second question is a lot of reference, but it's something recurrent in that study of Kantorovich metrics and dynamics, is there a way to deal with actions of infinitely generated groups? Because the examples I have here, they're really close to that, like actions of finitely generated groups, and here very close to that, hyperbolic groups. And the problem there is that when you deal with actions of groups and spaces, you also want some kind of metric of the group. Okay, and if you have a finitely generated group, you can take the length, the metric being the word length. You have generators, and you count like what's the shortest way to write it. But if it's infinitely generated, I mean, there's no clear way of what to use. And we'll come back to that. And yes, so this talk is basically about these two problems, and it offers, I would say, a solution to the first, and a suggestion with many non-trivial examples for the same. And in the process of trying now to try to find nice differentiation on metric spaces, one could go to Laplacians. Okay. So what's the Laplacian? Well, it's the second derivative, and you can do lots of stuff with the Laplace operator. For instance, you can make sense of the heat equation and solving it through school machinery, the derivative and space. Yes. You end up getting this solution that depends on time. Okay, and it really tells you what is, like, if you heat up a point X in your space, what's the probability at time t that it's to be transferred to Y. Okay, and this decays exponentially, as you see here. And as time grows, as I said, like decays, as time grows, you see here, like for this t, the blue one, the first one, it's very concentrated at around 0. If you take x to be equal to 0, it's very concentrated there. And as time t progresses, diffuses. And you can also view the time as variance. And moreover, you can make sense of Brownian motion. For instance, if you start with point x, then you have this Brownian motion, and then you might wonder what's the probability that it would land inside some nice set A. Okay, and you can measure this on the nose as soon as you know the solution to the heat equation. So you basically integrate the solution. So x is fixed. You integrate the solution over y on the set A that is of interest. Okay, now you're on a manifold, Riemannian manifolds, you have generalization of this operator, the Laplace-Beltrami, second derivative again. And now, if your manifold is compact, then you know that the operator delta is generalizable with discrete spectrum, and you have 0 as being a single eigenvalue, and then all the others are positive and grow up to infinity because it's an unbounded operator. but it has finite multiplicity, and therefore you can use, you can write abstractly the solution to the heat equation using the eigenfunctions and eigenvalues that you have. But now the problem becomes like, okay, can we find a formula for that, like as before? And one can most of the times do asymptotics. Okay, but still you can learn a lot of stuff from the heat kernel. It's asymptotics. For instance, A1 is basically a scalar curvature, or like 1/6 of A1 is the scalar curvature at the point X. Or through the asymptotic behavior of the eigenvalue. So you have this Calvin function, eigenvalues up to some fixed lambda. This is a function of lambda, and you take these asymptotics, and then you end up covering the volume of the manifold. And you can do also other stuff.
So my what is PT in the context?
I'm sorry?
What is PT? PT. What is
Okay. PK.
PT?
PT.
What's
This.
in your
It's exactly the same, like the probability that you hit at X and at time T, the heat does really squat. It's exactly the same. But of course, you cannot understand everything about the manifold from the heat kernel, and that was Kat's like question: can you hear the shape of the drum? The answer is no, you cannot. Just from that, but you can hear it if together with this spectral data, you have also the algebra of observables, like smooth functions, and the interplay of the spectral data together with. And this brings us exactly to noncommutative geometry. And yes, so today I'm gonna show to you that from spectral data and Laplace type operators, except for all this stuff, you can also do optimal transport in terms of you can get optimal transport like Monge Kantorovich metrics in terms of spectral data. And now this brings us to fractional Laplacians. So fractional Laplacians, why? There are many good reasons. One of these is that on metric measure spaces like a Cantor set, you cannot have an honest Laplacian because it's too many derivatives. The actual reason is that it's a local operator in the sense that the value of the Laplacian applied on the function f at the point x really depends on the values of f around the point x. And the Cantor set, because it's too disconnected, you cannot have this. You should look for non-local behavior, like the operator you're looking for, this non-local operator applied on the function f, evaluated at the point x, should depend on the global structure of your space. And the second is that, as I said before, here, just having an operator through its spectrum to understand the metric structure is not enough. You also want the interplay with function in the space. In particular, to have these operators, the commutators, to be bounded. But if you put an honest Laplacian here, like a second order differentiation, this operator will not be bounded. It's too many differentiations. Okay, so you should look on something that it is of order 1, like 1 differentiation, or lower orders, which brings us to pseudo differential operators framework. And that's why the right operator to understand something about metric space is the fractional Laplacian as a whole. Okay, it doesn't mean that every time this is the best operator. But if you want to look on metric measure spaces that have like counter sets and differential manifolds, you know, as the subclass, this is an operator that can be applied for. And the fractional Laplacian is basically the alpha power, the alpha fractional power of the classical Laplace operator, but now something magical happens. You end up getting this integral formula. Okay, for the fractional power. And this is a non-local operator. You can see this, for instance, you can assume that f of x is 0. Then delta fractional Laplacian applied that f of x, you can just remove this, but then it will be an integral to the rest of the space. Of course, there's some decay here. I mean, the further away you go from x, the less it will play a role, but still plays a role.
Okay, the problem is that delta is unbounded.
It's unbounded.
For alpha less than 1, delta for alpha will be bounded operator or
For alpha equals 1?
less than 1.
No, it's always unbounded. It's always unbounded operator. And it's always unbounded. And if you put alpha equal to 1, then you end up getting the classical Laplacian, as I showed like 2 slides before. But for alpha smaller than 1, you end up getting this integral formula. And you cannot have this integral formula for alpha equals 1.
Yes.
Because it just breaks down. All right. And now going to metric measure spaces. So one can therefore start with the metric measure space x du and writes down this integral formula as we had before. Instead of Rn, we have x. Instead of n, the dimension of Rn, we have a Ahlfors dimension, and mu, it's our measure. And we also require, I mean, this can be generalized, but this framework is already general enough to, at least for what we're interested in. We also require some compatibility between the measure and the metric, namely the volume of the ball of radius r has to be bound above and below in a uniform way of r to Ahlfors dimension. This is Ahlfors regularity, and there are several trivial examples, like Riemann manifolds have these, like several fractals, hyperbolic dynamic, uniformly hyperbolic dynamical systems, and Gromov boundaries, hyperbolic, yes, and limits of finite groups.
I have a silly question. So the f, I mean, the f is just a constant. It doesn't. It's not related to f.
No. No, it's just a constant. I put it there.
Where does f come from?
Fractal. The idea is that whenever you have such a measure compatible with the metric, several fractal dimensions coincide. Okay, and so on the metric measure spaces, as I said, you can have Laplacians, but not to all of them, like honest Laplacians, like second order differentiation, like local operators. And so when you start going, fractional, you can write down these formulas. Of course, if we are here in Rn, this delta lower alpha will be the alpha fractional power of the honest Laplacian. But as I said, in general, we don't have Laplacians to take fractional powers. Okay, so you focus on this formula, that always makes sense. And I mean, for alpha equals 0, you cannot just simply take this is defined for alpha greater than 0, the smaller than 1 or 1/2. Okay, And if you take alpha equals 0, it has a very different behavior. It has logarithmic behavior. I've given a talk here about this like last year. And you end up obtaining conformal structures on the metric measure space. But for alpha between 0 and 1, I mean, our work is to obtain some intermediate geometry, which is a bit deformed due to the alpha parameter. And when alpha reaches 1 from the left, becomes more and more and more local, in the sense like more classical, but never platform. And let's be more precise. How should we use this operator to obtain Monge Kantorovich metrics?
So you write here 2 alpha smaller than beta.
Beta. Beta is the folder regularity of. So you can do it more generally. But you can think always of beta equals to 1, like Lipschitz functions. And why, I should explain why this makes sense in Lipschitz functions. Because if you take a Lipschitz function f, and you take the absolute, you put absolute values on this and you put it inside, df to alpha x du y, this is less than or equal. I mean, you get the Lipschitz constant outside, and 1 over distance of x and y df plus 2 alpha minus 1 duy. And now you know that this is smaller than 0. Okay, from the assumption. And then, because of the volume control that you have on the measure, this is finite. Okay, so how can we use this? Well, the first non-trivial result is the following: is you start with your Ahlfors regular space and you focus on this triple of data. So you have your, just think of Lipschitz functions here, okay? You have your Lipschitz functions and you view them as operators acting by multiplication on L2 of x. And then you have the fractional Laplacian, okay? And the following is true. So you have, first of all, just focusing on the third bit, you have a complete control on how the spectrum of the fractional Laplacian grows. You have a Weyl law, okay? And asymptotics, in other words. Also, you know that the kernel of it is just the constants, and the image is just the functions in L2 that integrate to 0. Okay, so this is not a difficult thing to show. The most difficult thing is the following. So if you take any Lipschitz function, h, and any function f, again, Lipschitz, and you compute the commutator, as I showed, you end up getting an integral operator. Due to the regularity of, although you have a singularity here, 1 over x, 1 over the distance of x and y, the fact that you multiply with a Lipschitz function, which is regular enough, it makes this at the end a nice kernel. Okay, so that's not difficult to write down. The difficult part is to show that you can lift this identity up to the maximal domain of the operator. Okay, because the maximal domain is a domain which is like larger than any Lipschitz or older functions. You take some closures, some Sobolev norms. And you want to know that whenever you multiply a function A's being Lipschitz with a function in the maximal domain of the alpha that you cannot really describe in domains, you end up landing again in the maximal domain. So that's the trick part. And now, as I said, you have like asymptotics for how the spectrum grows on the fractional Laplacian on Ahlfors regular spaces. And yeah, one needs to use some embedding theorems by Lipschitz embedding theorems of snowflake spaces, and then use best of spaces there to do that. Okay, so there's some work here as well.
But repeat for F and H from the maximal domain.
Yes, so what one wants to show is that if you take H in a Lipschitz function and F being in the domain of this, then you want a multiplication operator by F, and the domain is L2. Okay. Be inside the domain. Yeah, so just just original.
But formally what you wrote is a weaker state.
It's a weaker statement, yes.
Because you wrote it here that you know that.
Exactly.
So that should not be too difficult. But
No. But this is a difficult part.
But the formula will still make sense.
I'm sorry.
If H is from the maximal domain, the formula is still holds, but the alpha.
Yes.
H is well, I know H is Lipschitz.
Yeah, it meant like F being the maximal domain. Yes, you extended it. But I wouldn't say it's terribly difficult, but it's quite non-trivial. Right. All right. So we're getting closer to answering Riefel's question here already, like natural differentiations on metric measure spaces. Okay, so the next one, which is the getting to the non-trivial, more non-trivial stuff, is the following observation that these commutators that I showed you here, these integral operators, they are in fact compact operators. Compact operator in a Hilbert space is one that its singular values converts to 0, and eigenvalues that it has are finite input list. Okay, so they accumulate to 0, the eigenvalues. And for instance, if you had an infinite diagonal matrix, it means that the eigenvalues in absolute, the value that converts to 0. So the entries of this infinite diagonal matrix. Of course, any finite matrix is compact operator. All right, so we get a compact operator, and not just that, we get that you have some control of how the eigenvalues go to 0 over these commutators. And this, I'm writing here that the commutator is in the Schatten-class of the Hilbert space. It means that the eigenvalues are LP, little LP small. Okay. And then, you have a very precise lower bound for when this can happen. Okay. You have the fractal dimension and the regularity of the functions that you take commutation with, that you try to differentiate, and the fractional parameter. Okay, and this is quite remarkable that this happens, because in the classical situation where here you had the Dirac operator in the manifold and you were taking commutation with Lipschitz functions, you end up getting, so as I said, in the classical situation, like you have manifolds here, and D is the Dirac. Basically, you would end up getting M H prime. Multiplication by the derivative of H. And the multiplication operator on a Hilbert space is not compact unless it's supported at finding many points. So for non-trivial functions on a manifold, you can have that this is compact on Lipschitz functions only if the manifold has finitely many points. So it's a trivial manifold. Whereas here, we have something like to complete opposite from that. And okay, so one can write down this Monge Kantorovich metric, but instead of using the operator norm, we use the Schatten norm. The Schatten norm is basically the LP, little LP norm of the singular values of the commutator. And the reason for doing this is because, well, first, it feels quite natural to use this additional information. Second, these certain norms are more sensitive to the spectrum of the operators, and therefore they should hold more information. Okay. And yes, so let's see what we get from here. And indeed, this spectral data that I showed before, like Lipschitz functions, fractional Laplacian, and this Monge Kantorovich metric that uses this additional analytic regularity of the commutators. This metric gives a weak star topology on the space of Borel probability measures on your space. In fact, you can control how the metric relates to the original metric. We have some like information here, which is to be expected for the fractal parameter, and here's the regularity that of the functions that you commute with. You can think of beta being equal to 1. And the idea showing this the fact that the metric generates the weak star topology is the following. So you focus on these semi-norms. The upper bound, it's not easy, but it's not the difficult part of the proof. The lower bound, however, is quite challenging to show. And why is that? Because going back here, what do we want? If you can think of this as like some abstraction of Lipschitz functions, and if you have a collection of Lipschitz functions with Lipschitz constants bounded uniformly above, then it's equicontinuous family. Also, in this formula, you can just focus without changing anything on functions that vanish at a given point. Okay, where they vanish at some x0. It will not change the formula. So you end up getting a uniformly bounded, because we have assumed it's a compact metric space, uniformly bounded family and equicontinuous family. So you have as the last colleague, right? And therefore you get something relatively compact. And this is the essence. Oops. In showing that the metric generates the weak star topology. And by getting such a lower bound, by something that, so if you focus on functions H that this semi-norm is than or equal to 1, then you know in a uniform way that the folder to alpha semi-norm will be less than or equal to 1. So you can apply that as the last column here. But obtaining this lower bound, it's difficult. And the main steps is that first you take your metric measure space and you decompose it into dyadic cubes. Like in dynamical terms, if you had here a hyperbolic dynamical system, you would decompose it into Markov partitions. And you take a Markov partition, you refine it to a smaller Markov partition, and you keep going. So you basically approximate your space to finite means. Not actual means, but I mean in a finite way. But then you use means, yeah. So and then using this dyadic approximation, you want to start getting lower bounds for this semi-norm. And so you have this, basically you can do it as a rooted tree. And the first level is the vertices in the first level are the cubes, like Borel sets your metric space that partition your space. Okay. And then you have the finer cubes in the finer, and this gives like a tree structure to inclusion at each level. And you can take the expectation of your function x, h at each level. And in LP space now, and you end up getting such lower bound. And then this is only an intermediate bound, and then you can bound this uniformly below by some Sobolev norm of the metric space, and then you can show that you can use the Sobolev embedding theorem that gives you that it just matches exactly like the parameters, like it was meant to be used that way. And then you know that this Sobolev space embeds continuously in the folder 2 alpha, and this will give this lower bound. Yeah. And therefore you can use as the last volume.
Do it on the interval 0, 1.
Yes.
Does it become much easier, or the difficulties are always?
It's the same. It's not much. Yeah, there are some parts that will be easier. Yes. There are some parts that will be easier. But I would say like 30% models, something.
But exactly the one.
Just the same estimate. Like, yeah, like exactly the same statement, but not in the context of abstract measure space, which is not regular, but very concrete.
But what you could probably do, like for the interval, is like you could piece on the nose.
See, I mean, as Dimitris was saying, so quite a lot of this abstract Ahlfors regular structure is because actually have these results that you can put this into Euclidean space, you know, like in some sense.
If you snowflake, if you take fractional powers from the metric.
But wondering how much
of
the difficulty remains once you are.
Yeah.
But was it known for say 0, 1 or something?
No, this is a completely new observation. And in fact, obtaining spectral triples with compact commutators. I mean, the only way to obtain compact commutators before was to use functional calculus to force dampen down the spectrum of your operator, but this is like geometrically doesn't have any meaning of doing that. But having a natural operator that gives you exactly that, that's on this general framework. I mean, that's the interesting part. Okay, so we end up this way getting like Monge Kantorovich metrics in a very general situation. But how can this be used? Well, what is the best Schatten-class? P equals 2. What does it mean? It means it's the compact operators with singular values being little L2 summable. And why is that? Because little L2 is a Hilbert space. And whenever you are in a Hilbert space, everything becomes so nice, so symmetric. And the following, and sorry, going back to this slide, for this line, when, so I'm saying like focusing on metric measure spaces, so that this metric, we take this metric, but for p equal to 2. But of course, we need the commutators to be to have these singular values being able to summable. But also we have a lower bound for when this can happen, which depends on the spectral data of the on the dimensional data of the space. So on very small dimensions, you can do that. But this is true that you can do this on very small dimensions because you consider all older functions. So if you potentially could take a smaller set, but without changing the metric, then you might be in business into getting Schatten-class, commutators in S2. And this is indeed the case when your metric space admits diffusion, which is point recurrent. I will not go into that. I mean, this is measured through some other dimension called spectral dimension. And this is equivalent to saying, basically saying that the spectral dimension is less than 2.
How it's related to this dimension you introduced before?
It's to the Hausdorff dimensions. Yes, it's really this. Maybe right here. So you define the spectral dimension as 2 times df minus something called the walk dimension 2 n. Yes, that's correct. So for manifolds, the topological manifolds, this is equal to n, let's say the dimension. And for topological manifolds, this walk dimension that measures the mean exit time of a random walk from a ball of radius r is equal to 2 all the time. So you end up getting the topological dimension. For total disconnected spaces, this is infinite because you get trapped in the cylinder sets. And so this is going to be 0. For several fractals, this is going to be less than 2. And so if you ask for this to be less than 2, it's equivalent saying that the fractal dimension is strictly smaller than the walk dimension. So you don't need necessarily to have a disconnected space, but you won't have many poles. Okay. And
so I have a question. So what does the alpha measure? Bit of alpha means?
I haven't written down the formula for that, but here's the idea: like whenever you have metric space with this point recurrent diffusion. By the way, when PS is greater than or equal to 2, the diffusion will never, almost never returns to the point. It's the drunken mathematician, okay? But in fractional setting. So you focus on your fractional parameter and the fractional Laplacian, and you write down this Monge-Kantorovich metric that I showed in the previous slide. And then you observe that if you consider a fractional Laplacian of higher order, so let's say you take here 1/4, you go up 1/2, something like that, then you can use the spectrum of that fractional Laplacian so that the Monge-Kantorovich metric is given as a series of spectral data of the higher order fractional Laplacian. These are the eigenvalues and the eigenfunction. And I've given several talks about this and asked people. I mean, this seems to be the first closed formula for Monge metrics. And the nice thing about it is that it's totally computable. In fact, in practical terms, if you want to measure the distance of probability measures, you don't need the full sum. You just take a finite part, and then you know it decays fast enough to asymptotics or the Laplacians.
But it's better you need to define by
Yes.
something.
Yes.
Take larger better good number.
Depends on the context. Depends on the context. Okay, and so you have several examples from GSS of circular groups with this property or like the natural fractals in any topological dimension. Doesn't mean that the topological dimension is small, it can be whatever. Okay. Anyways, so I will come back to that later on to show you that it is indeed computable. And of course, you can have dynamical versions of it, and I will explain. Anyway, and then you can abstract this and look for this triple data, that spectral data that you call spectral triples, and you can abstract this to sister algebras, and then you can ask the commutator to be in Schatten P, and you can go even further. So having singular values in this little p, it's not the only behavior of singular values for compact operators that you can find. You can have other decay rates. Okay, and symmetrically different ideals like Dixmuir stuff. But I won't go into that. But you can abstract it. So let's go to dynamical settings. Okay. And I have until
12:45.
Okay, great.
25 minutes.
Great. Okay. Any questions so far? One question.
So before you consider the commutative algebras, now we will.
Yeah, we go to non-commutative stuff because you put dynamics. So allow me to go to the start. We will start seeing this like orbit spaces. Okay. And yeah, and try to define Monge-Kantorovich metrics on these spaces. Now, how should you view this? Again, informally speaking. Okay, so if you have a metric space, you can talk about the probability measures, and you understand what we understand easily what needs to measure the distance. Okay. But if you have the dynamics and you're like, okay, let's try to find Monge-Kantorovich matrix for probability, abstract probability measures on this dynamical system. What does it really mean? The way I like to think about this is somehow as a space-time. Okay, informally speaking. So you have your space X, and you have your time given by the group. It's the symmetries. So yeah, think about like we try to put Monge-Kantorovich metrics on different space times in the space. But first, one needs to see how to get these Monge-Kantorovich metrics on just groups, okay? Because we see how to get them. We saw how to get them on spaces. We need to see how to get them on groups and then glue them together, okay? Because the group acting on the space, so you glue these two Monge-Kantorovich metrics together. And this is often done through the following. I mean, this is the definition that we give, and I will explain what's the new part. The length function on a discrete group is such a function, okay, to the positive numbers, 0 only at the units, symmetric, and you also want it to be proper, meaning the inverse energies to be finite. And we ask, and usually in the literature, the requirement was that for any fixed gamma, if you define this translation function, so basically you act on an element of the group eta, the gamma is fixed, and you take the length of eta minus the translated length of eta. Okay? You want this to be a bounded function. Here, we want it in general to be p-summable, and it will be bounded if p is equal to infinity. Okay, and then we can start getting a differentiation on the discrete group through this length function. And the differentiation is really given by the following operator. So first, you take like finitely supported functions of your group f, and then you multiply them entry-wise, point-wise with the length function. And the differentiation then is given by taking any element of the group algebra, lambda gamma is translation by gamma on L2. Okay, translation by gamma, and then you take the commutator with this length function. And you end up, this is an algebraic computation, and you end up getting this. So whenever the length function has these properties, in particular is p-summable.
So lambda gamma f, that will be f of gamma minus.
Yes, so here it will be f of gamma eta, and then you have this exactly. But since if you assume now that this is p-summable, the translation p-summable, this is going to be an operator. This multiplication by this will be an operator with diagonal, right? With eigenvalue going to 0 in LP way. And therefore, you end up getting commutators in the Schatten-P. Okay, but that's the definition. But can we find examples? Because all this time I showed you examples on the measure spaces, but this is discrete group, so it's like a different set. Well, here's a hands-on way to obtain such differentiations in discrete groups, and in fact, groups which are not finitely generated. Okay. So let's focus on abelian groups, but for dynamical purposes, I think it's like hyperbolic dynamics and stuff, it's fine. So you take a compact abelian group and we treat it with a metric, and it's going to be binary, and the parameter. Okay, and assume that it has this Ahlfors regularity. Now, the only cases that I can think, the only groups I can think that they have a hard measure which cannot be Ahlfors regular are groups with infinite topological dimension. I could say infinite products of the circle. I don't know. So I would say this is this can be made. It's a generic property. Now, from general theory that we proved about the fractional Laplacians, we know that the eigenfunctions are exactly the characters of the group, and these are Lipschitz as well. And so here's a way to get a length function on discrete groups through the fractional Laplacian. So the discrete group, you focus on the dual, the Potriagin dual, which is your discrete group. And we know that every such element in here, which is a character, okay, it's an eigenfunction of your fractional Laplacian. So you simply send the character to the associated eigenvalue in the Laplacian. Okay, I mean, at least for now, this is a function, a well-defined function. But it turns out to be such a length function as I showed before. And it is p-summable for p greater than the fractal dimension of your original group over 1 minus 12, and the 1 comes from the fact that you deal with Lipschitz function. You could do it for all the functions, but why? I mean, they are already Lipschitz the characters, so. And you see that you end up getting, somehow you have the discrete group. You look at its Potriagin dual, which is a compact metric space. You have the fractional Laplacian, and through Fourier transform, you transfer everything back to the discrete group, and you end up getting these formulas.
So what happens? What are exactly the formulas when X is just a torus?
There you can be more specific.
Sure, but then that should be surely something known. That will not be a very complicated formula, right?
Ah, yes, but as far as I know, I haven't seen it.
By which I mean you can just write down what.
Yes, definitely. You can be quite specific.
For example, the circle.
On the circle, the eigenvalues, I mean, they're. So the issue, I mean, you can compute everything. I have computed them. It's just I don't remember now. Maybe I should.
I just wonder how different will this alpha be from the usual length?
Yes, I can give you that. So on our end, then the fractional power of the actual Laplacian is this. On the circle, this is not this. Because this has a semi-group property, this doesn't. You can measure, however, how close these two are. And they are pretty close, up to some Schatten operator, the difference. But they are diagonalized on the same basis. It's just the eigenvalues are different, but it's not, the eigenvalues of these are not simply the eigenvalues of delta, it's the fractional power. So you really need to compute the integrals. But it's totally doable for Tori. I just don't remember.
Maybe one more comment because you just said okay, that's great. That's great because we don't need finite generation.
Yes.
But then you also told us that for these examples which really can be generated, you probably do not have Ahlfors regularity.
No, in topological dimension. For instance, if you focus on the dyadic solenoid,
okay,
the dual is not. And you, in fact, you can also compute stuff there. Yeah, so
some cases.
yeah, that's a good point. But these are highly, I mean, you can either be finitely generated or infinitely generated, but I would say very infinitely generated, I don't know. Yes, and so what are some interesting examples of dynamical systems that one can apply this stuff that I showed you today? Well, focus on this abelian group, but now assume that it admits a Z to the M action. It doesn't have to be from, one homomorphism. A Z to the M action, so that the action is expansive and strongly mixing with respect to the Haar measure. Then you can define the homoclinic subgroup of your group. And what is that? It's really all the points in your group that if you let the dynamics go to the future or in the past, I mean, here you have n directions, but think of m equal to 1, okay? But if you let the dynamics go to the future or the past, they converge to the unit, okay? This is a discrete subgroup of your group. And due to expansivity, basically, and you can show, but this is not a trivial thing to do. I mean, it's work of Dimitris and really nice papers, and it's a whole topic on its own. But they have a sheet as a book on algebraic, dynamical systems of algebraic origin. So you can find all these in there. This is isomorphic to the Potriagin duo of the group, the homoclinic. So you have the group X, you have a discrete subgroup in it, and that is isomorphic groups to the Potriagin duo of the big group. And an observation that we make also in the work is the following. Observation. Well, this is clear, it is obvious. So if m is equal to 1, and then you have some other properties, shadowing properties, the dynamics, like some hyperbolic structure, uniform hyperbolic structure on your dynamics, then this is going to be a Smale space. And yes, and now if you focus on this system algebra, basically the action of the homoclinic group on the space, this is for Smale spaces. The Weyl homoclinic system algebra. Weyl didn't define it in that way, he defined it as some foliation. But because you deal with groups, you can turn the foliation into foliation coming from a group action. And what we have so far is, for instance, but of course this system algebra makes sense not only for Smale spaces, meaning m equal to 1, but for this general situation. So what we have is the fractional Laplacian on the coefficient algebra. We have, through Fourier transform, the fractional Laplacian data on the homoclinic, because you can put it back to the Potriagin dual and then use the isomorphism to go to the homoclinic. And we want a way to glue this information together. And this comes from this theorem here. So this gluing has been really, I mean, this general gluing has been pioneered by this Scandinavian team. And I will not try to pronounce their names because they are not read as one might think. Every time I'm doing it wrong, you know. Yeah, I know the first, like Alsa. Yes, we call it. Yes. So they have a general recipe on how to do this gluing. Okay, but our contribution to this general recipe is that this recipe worked whenever you were considering operator norms. But here we deal with Schatten, it's not sister algebras all the time. And you have to go really into functional analysis and tensor products for Banach spaces and pure multipliers in order to do that. So something non-trivial, but the idea is the following, that you have a compact metric space and you act by an amenable group, countable discrete on your space, And you assume that this space, I mean, the continuous function from the space is equipped with some semi-norm in the sense of real. It doesn't have to come from the fractional Laplacian. And you also assume that the group is equipped with such a length function, like a proper translation resolvable function. So I gave the definition. And now one can define a semi-norm on the functions that have domain, your discrete group, and coefficients, some dense subalgebra of C of Z, of Z. Okay, like Lipschitz function, like that. And you have now two semi-norms that do the following. So this vertical semi-norm basically looks at C of yes. So looks at looks it takes into account the data of the discrete group and sums them over the space Z. It takes the supremum over the space Z. So on the discrete group, we have assumed some semi-norms. So you take the supremum, and the semi-norms depends on Z basically, and then you take the supremum, and the horizontal does the opposite, but you take the semi-norm on here, you take the supremum of its dependence over here. But it can be made very precise, but let's not focus on that. The idea is that you can glue these semi-norms and then write down Monge Kantorovich metrics for these objects, not just the coefficients of the group. Right, so you have for dynamical systems, which can be made quite explicit if you work with the circle, for instance, here, or tori. Okay, and some future works. For instance, what is it? So you can try one thing that I find quite interesting is this closed formula that I showed you before. This one here. And this works, this converges whenever you have this point recurrent diffusion around the walks. Okay? And try to find similar formulas for when the spectral dimension is greater than or equal to 2. But this will involve LP spaces now, not L2 spaces, and we need to work out dualities. And also, since we have computable metrics on the spatial probability measures, I think it's important to try to make sense of geodesics with respect to these metrics. Because it's one thing to know how costly, let's say, or how energy does it require to transfer a probability measure from one place to some other. And another thing to know, like, what's the best way to do it. And moreover, these operators that I showed you, like the fractional Laplacians, they give a lot more information, like you can make sense of symmetries, isometries on your cross products here. Because you have a notion of differentiation, so you kind of start viewing this as a manifold somehow. You have a differential operator acronym, pseudo differential operator acronym, and then you might wonder what kind of symmetries and isometries it gives rise to. Because classically on the manifold, the isometries are defined as the homeomorphisms that leave the Laplacian invariant. So you can start asking these questions as well for these dynamical systems. And these isometries will be given in terms of spectral data. And this is, I'm going to work with Adam here. And okay, maybe since I have 3 minutes, I can show you some Python illustrations because I said I will try to convince you that this is indeed a computable formula. It's computable because you no longer need to do optimization. It's not the supremum of some quantity or the infimum. It's just there. So as soon as you know the spectral data of your space, you have the Laplacian and you can diagonalize your fractional Laplacian. You write it down and then you integrate. You put the measures and you integrate. You end up getting a number. Now, what the number is, like the distance, depends on the problem you're working on. Okay? But at least you get numbers. And quantitatively, this gives you a way to get to see whether 2 measures get very, very close or very, very far away. Okay. So these are dumb examples, but you can really do this. So you take the interval, and just here we generate some random normal distribution and with different variants. So this is more spread than this. And here you have the overlap. Sorry, here with the third part we have the overlap, but the overlap doesn't mean it doesn't give the distance. Okay, so we have the overlap, and then where do I have the distance? Here, very small. So the distance between these two, the first two, is 0.22, which is not really the cost of pushing the second, squeezing the second to the top to then the first. That's really the energy, even in terms of Laplacian. And on the other hand, we have these two. I mean, they are the same, but in different places. There's no overlap. Okay. And the distance is 0.41. So here, all the energy is like pushing, translating. Okay. You don't need to have the same family, work within the same family of distribution. So you take a beta and you take normal. And again, I mean, you try to shape either the first to the second or the second to the first. And you will need like 0.30, 0.3 energy. Or you have like almost, point masses. And the distance is 0.97. I mean, if I put it a bit more to the side, it would be 1.
So if you shift just one and check another, the distance will not be equal to how much the shift from something.
No, in principle you can compute how things change, but I haven't done.
Yeah, you shift in the delta method. Yes, that's the assumption, right? But from right, but it's as long as you have some structure around it.
Yes. And another interesting thing that I found after working in this Python stuff is the following. So you see here it's 0.97, whereas the metrics are given, they're not normalized. There's no real reason to be between 0 and 1. So how do you know what's the right number to normalize? That's not an easy thing. But what you know is the following, that the spatial probability measures, I mean, I just say, the spatial probability measures is convex. Okay, so you just need to focus on the point masses because they're a convex combination. If you take a closure, it will give you the spatial probability measures. And therefore, from Trial-Nilman, since you have a metric and not just something pseudometric or something, since you have it on the nose a metric, you know that the diameter, the spatial probability measures, will be given by the diameter of the point mass. So you can just work it out, and this will give you the diameter and the right constant to normalize your Monge-Kantorovich metric. Okay, but you can do even more. Like you can start getting rates of convergence between probability measures. But again, dumb example, but it's illustrate. So you take the normal 0.5 invariance, 0.1, 1 minus 1 over t, like something that converges to 0.1, and you end up getting this. Okay. So the interesting thing is that you get numbers, and so you can do some regression and end up getting like the distance changes over t as 1 over t. Or you don't need to, it doesn't work only changing the variance, but you can also change the mean. Okay. And the reason I'm thinking about this is because let's say you have a sequence of measures and you don't know like how the convergence happens, and you need to do some theoreticals to prove some theorems, and so how you put it in the program. Then you will get some behavior, so maybe it will give you a good idea of what to expect. And you can do even more. For instance, you can take a number, irrational number or rational, whatever, or transcendental, and you can look at the decimal expansion. Okay, so it's a sequence, symbolic sequence. And then you can view the symbolic sequence as a probability measure on the shift space of 10 symbols, 0 up to 9. In fact, you just go here to this formula, and this formula has a bit more information in it, in the sense that you can just, okay, so if you truncate up to some n, basically you can write this formula. This eigenvalue has some multiplicity. Okay, so you take into account all the eigenfunctions of that eigenvalue. Okay, so if you go up to the 10th eigenvalue and you take into account all the spaces, the eigenspaces, don't chop the sum before that, and then you can, and you take all the different chops, like you can focus on frequencies, like the nth frequency Monge-Kantorovich metric. Okay, and then you have sequence of metrics. So you can do this, and if you take the nth frequency Monge-Kantorovich metric, you keep going, it's going to see like finer and finer and finer structure of the distribution, probability distribution, and this is what I have done here. So these are the frequencies, and this is the distance of t from 0 through the different frequencies, like what the frequencies see. So you get some pattern, it's not periodic. And after doing this, I was like, okay, maybe I should do something on periodic. Like, would I get something periodic? And indeed, you get something periodic. If you take this number and you compare the distance from 0 using these Monge-Kantorovich metrics, you end up getting this. So this has period 10, and the amplitude changes because of some other dynamical stuff, but it's periodic. Yeah, DNA sequence, I don't know. Yeah, in fact, I did that, and I got the distance between human and a banana. Yeah, some genes. I don't know. But yeah.
The answer.
What was it? It was like, I don't remember the gene, but there's a library. It was 0. It was. No, we were quite close. Like, no, we were like, no, what was the distance? 0.3, the distance, and the maximum was 1. Like, no, 70, 60, 70% the same. No. Anyway, thank you.
I have a question. So, is there any chance of going beyond the Ahlfors regular case to something like maybe not at every point, but almost every point? And maybe
yes.
only the local dimension.
Uh-huh. I think so, yes. But this will be more elaborate, but you need to keep track of these irregular.
So this would, for instance, I think right away give you a larger class of fractal objects. For example,
Yes.
overlaps.
Yes, exactly.
Okay.
Exactly. Yeah, I would be interested to see something in that direction. But because not all limit sets of finite groups are Ahlfors regular. So yeah. So that interesting.
If there are some questions online. So it's not very that spending too much. Next week, we will